Yeah, that's a tricky point because I at this time it's really hard to find sensors that can do all this multimodal sensing, right? Both temperature, shear forces, pressure forces, and so on. So I think this is actually an interesting point that you raised, because I believe that at the moment we're seeing a lot of development of different sensing technologies. We have very good temperature sensors. We have good sensors that can estimate forces. Other sensors that are pretty good at detecting fine texture of external objects. And like one could ask whether we could combine the advances in all these different sensors. For example, if we have a multi-fingered hand, can we combine different sensors such that we kind of retain this multimodal information from all the sensors? Can you include more and more sensing skills inside the same sensor, within the same sensor? And the other one, so how can we use state-of-the-art fabrication techniques of soft materials to come up with very complex tactile sensor shapes, and how can we efficiently sense forces or any other quantity over complex shapes rather than the usual flat shape or like slightly curved shape that we have so far.
In this podcast, I'm sharing my passion and curiosity for soft robotics, where we share inspiring stories about the work we do and how we can push the limit. I am Mara Dwini, and this is Soft Robotics Podcast. Support for this show comes from Science Robotics Journal. I really find Science Robotics to be a great resource for reliable and tangible research where we can really push the limit of the science we do in robotics. Great way to stay up to date with the published article is checking out the released monthly issue. All the links will be included in each episode description. We will also happen to have a regular conversation on the most published science robotic articles, where also you can contribute with your question and thoughts about the research. Thanks Science Robotics for sponsoring Soft Robotics Podcast. So maybe firstly, I would like to ask you how you would like to define yourself for people first time listening to you.
Yeah, I am a robotics researcher, specifically with a focus on data-driven tactile sensing. So I just completed my PhD at ETH Zurich, where I was advised by Professor Raffaello D'Andrea. During my PhD, I have first worked on the design and the fabrication of vision-based tactile sensors. Then I worked on a data processing framework to extract relevant quantities from these tactile sensors. And finally on applications of tactile sensing to robot control, with my latest focus being on the transfer of knowledge from simulation to reality.
Great. So I think your talk in TEDx Zurich was a really great talk, and maybe anyone listening should listen to it.
Thanks.
Maybe I think what I would like to ask you here, when it comes to soft robotics, what is your thought about sensor design? What's maybe you think from the journey you did in the research, what is maybe missing questions, or maybe still missing in sensor design in general, before going to tactile sensor design?
Yeah, that's a very interesting question, because I think sensor design is not a trivial task, and the reason is that when you design a sensor, there are not just two variables. Let's say you want to optimize cost or optimize the sensing accuracy. There are so many variables that are even hard to think about when starting to design the sensor. And I'll make you maybe make some examples with vision-based tactile sensors. So the sensors are sensors that use a camera placed in front of a soft, transparent material, usually a membrane, and kind of try to track the deformation of this soft material. So the clear benefits of these sensors are the fact that they have very high resolution because they use the high resolution of the cameras, and they are low cost because essentially it's just a camera and some soft material. But there are other two advantages, more on the practical side, that are often not mentioned. And the first one is ease of wiring. So usually you just have one cable, usually USB cable, to collect the data or extract the data from such sensors. And this is very important when you think of routing cables around a robot that is moving around. And the second advantage is even more practical and I think even more important. And it is the fact that to fabricate these sensors, you only need very basic knowledge, like silicon casting knowledge. And to use them, you need computer vision expertises that are already present in the robotics lab. And this, in my opinion, is a terrific deal breaker.
So maybe there's two approaches here. You use vision-based camera here to sense information, and maybe other way to embed sensing in the material, and we still have a limitation. When you view the two approaches, you mentioned now the advantage, but if you have a general perspective about two approaches, embedding sensor or external sensing, how do you view that from what you have been done so far?
Yeah, so I think, as you said, there are different approaches, right? Vision-based is just one. There are other approaches. I can think of the classical capacitive or resistive tactile sensors that have been used so far. I would say that there is not yet a comprehensive solution like cameras are for the vision community. But I think there is being a lot of effort on different sides, on different approaches to tactile sensing. And what I've been trying to do in my work is also to find like common representations between the different tactile sensing principles, such that once we build up results on this, based on these representations, that this could be also transferred from sensor to sensor. At some point, maybe there will be a clear winner. We don't know when. Maybe it will come from outside the robotics community, because there is a lot of work on force sensing in general. But I think for now, we need to all push in the same direction. So probably working on some intermediate representations and make really the results transferable from sensor to sensor.
Mm-hmm. So I want to ask you, what makes a good sensor design? You mentioned that using vision here, camera, to see how the deformation of the material. Can you lead us about the material part? What kind of learning you do to understand how the material behave or deform, and then you can estimate the forces, or what kind of sensor you try to sense, like force, pressure, touch? What makes a good sensor design here?
Yeah, this is a very interesting point, because I believe that there are two ways of approaching this problem. One is to get a sensor that gives you, by design, very clean or useful sensing output. And this is usually very hard to achieve. So one way of compensating for this is to have a bit more elaborate data processing that can take the raw tactile data and try to estimate more high-level quantities. So you mentioned forces, for example. What we have been doing is to convert this raw tactile data into a map, essentially a matrix of forces in 3 dimensions. So we could estimate in this way both the shear components of the force as well as the pressure component of the force. And we believe that this is kind of very general because from this representation, you can detect the contact locations, because you have essentially, like I said, a map of forces, a map of 3D vectors. And in this way, you can detect where the contact is happening and where there is no contact. But you can also retain information about the magnitude of the forces. So where I'm applying more force or where I'm applying less force.
Mm-hmm. Maybe I think it's what was interesting. I think we speak about the sensor architecture, or how we, for example, you mentioned the lattice, for example, this matrix, and then you sense the contact point if we embed the sensor. But when it speaks to your way, the accuracy level, because sometimes we try, if we embed the sensor, try to play with different morphology or architecture, that we can have accurate data. From your way, how do you think you can push the limitation of accuracy when it comes to the data of the, for example, touch or force?
Yeah, so I can tell you my experience that when trying to address this data processing part in a model-based fashion, so trying to extract maybe analytical models or use some numerical models in real time, the bottleneck was really on the real-time feasibility. So if you want to do this in real time, you usually get to compromise the accuracy of your measurements. So the way we have tried to approach this study is completely data-driven, which means that we collect offline using very accurate simulations, or even in the real world, a lot of data that is very accurate, because like we don't care about the real-time execution at that time during data collection. We just need to collect a lot of data, and then we train a learning architecture, usually a neural network, that maps the tactile output, like the raw output that we get from our sensor, to the quantities that we are trying to estimate. For example, this map of forces.
Maybe another situation, because if we imagine that you have different sensor at one structure, like you want to sense, I don't know, the touch and force, maybe temperature, something, maybe sensing different sensor signals. How this could be achieved to distinguish this is the right signal for each sensor to detect, like force and temperature. Do you have a situation like that?
Yeah, that's a tricky point, because at this time it's really hard to find sensors that can do all this multimodal sensing, right? Both temperature, shear forces, pressure forces, and so on. So I think this is actually an interesting point that you raised, because I believe that at the moment we're seeing a lot of development of different sensing technologies. We have very good temperature sensors. We have good sensors that can estimate forces. Other sensors that are pretty good at detecting fine texture of external objects. And like one could ask, one could ask whether we could combine the advances in all these different sensors. For example, if we have a multi-fingered hand, can we combine different sensors such that we kind of retain this multimodal information from all the sensors? That's an interesting question, and it's hard to give an answer right now, but I think one way of addressing it would be really of trying to combine the benefits of multiple technologies into the same task.
Mm-hmm. So I want to know your view about sensor design in terms of robotics, from the literature, what you have been doing, maybe what's still missing from your research and maybe in the field. What's maybe still missing, do you think, in the design process?
Yeah, one is what you said, right? Multimodality. Can you include more and more sensing skills inside the same sensor, within the same sensor? And the other one, more on the hardware side, is really how can we scale this up? We've been doing some investigation, for example, using multiple cameras to extend the sensing surface, and it turns out that the models are actually transferable. So the sensing models are actually transferable across different locations of the sensing surface. But this is just still, research in the lab. So I think we need like kind of a stronger engineering effort to see how much we can push this, how much we can scale this up further. I think this will be an interesting direction. Another direction would be instead like more on the direction of large-scale fabrication. So how can we use state-of-the-art fabrication techniques of soft materials to come up with very complex tactile sensor shapes? And how can we efficiently sense forces or any other quantity over complex shapes rather than the usual flat shape or like slightly curved shape that we have so far?
Mm-hmm. For the shape, can you elaborate more how it's maybe significantly in the changing of the way of the design? If you speak about complex shape, other shape that we already traditionally see in literature. Have you ever thought about that?
Yeah, so you can imagine like if you just have a flat sensing surface, you just have to place a camera in front of it. And, that would be enough. You probably just covered in all the angles that you're interested in. If you have a shape which is a bit like more complex, let's say you have a spherical shape and you want to sense forces all over the sphere, you probably have to think about camera placement and how many cameras do you need, or like how can you minimize the number of cameras to observe with a resolution that is good enough to sense forces at all the angles.
So maybe I want to ask you, that's an interesting point that you mentioned, how to maybe the ratio of the number of cameras to make a good sensing. And I think that's an interesting part. Maybe I ask you what make a sensor maybe fail in the design. That make the sensor setup or design fail. Do you have encountered what makes the design fail when it comes to this setup?
Yeah, I think right now we're having a quite tough time in making these sensors thinner and thinner. So there are some results already on making optical or vision-based tactile sensors thinner, because you can imagine the main bulk is the camera unit, which is usually quite thick. But there are also very small cameras. But then the problems become the distance, the focusing distance between the camera and the soft materials that we are observing. And in this sense, the main issue is represented by the fact that cameras are designed for another task, that is take pictures. So I think that at some point we probably will see cameras that are designed for this specific task, doing tactile sensing. So where we are interested in having the largest possible field of view, as well as the closest possible focusing distance. Once we will see cameras that have these characteristics, I think that the design could improve even more, and we could make them really sensors with a very small footprint.
That's exciting. Maybe in this process, what maybe exciting moment, or maybe something, because sometimes the researcher found something very interesting or maybe counterintuitive what we saw about. Do you have any moments that's very exciting or surprising in this research?
Yeah, I can tell you maybe about a system that we have built about last year. So we essentially built a system that kind of resembles a classical inverted pendulum, moved by a linear motor. But instead of having a mechanically fixed pivot point, we had a two-finger gripper. Essentially, we had the gripper with two fingers equipped with two of our tactile sensors, and we tried to grab a pendulum with this gripper. And then by moving the gripper with the linear motor and adjusting the gripping force, we try to swing up the pendulum, performing a 180-degree rotation. Same applications as a classical inverted pendulum, but again, just with a gripper instead of a fixed pivot point. And we found out that the most reliable way to perform this task is by modeling the system in simulation, where we don't use an analytical model, but we use a numerical model based on finite element methods. And we could train in such a simulation a reinforcement learning algorithm. And we could use as well in this framework, in the simulation framework, like domain randomization, which essentially means we perturb the dynamics, the parameters of our dynamic system, such that the policy that we learn with our algorithm is kind of robust to these changes. So we could then apply this policy directly on the real world because the policy is robust enough, and we could swing up poles that differed in mass, diameter, or length without even knowing the physical characteristics of this pendulum. And so we really were thinking that once we transfer this policy to the real world, we would have to keep training in the real world, but this wasn't the case, and the behavior of the system was the right one already with a direct transfer. And I have to say we were really surprised, and yeah, it made us kind of even more aware of the power of simulation in tackling or addressing advanced robotics tasks.
Mm-hmm. That's a good point. Maybe before we go into this part, I want to ask you, in the setup that you mentioned, for example, if you have a robotic finger like gripper and the camera and the material for sensing here, the formation, how do you see this interplay between the movement or manipulation, and you have the soft material as a sensing, like, I don't know if you use silicon, for example, here to sense the formation by the camera. If there's any maybe challenging here, Bart, still significant limitation or drawback in this setup?
Yeah, I think the main challenge is there are two main challenges. One is modeling the dynamics of the soft materials involved in the process. And the second one is modeling friction. I think this is very challenging. It's been probably the most challenging part in our recent work. And so while for the second, we just need to work more on this and try to find the right friction models for performing the different tasks. For the first, I think that we kind of have one way of kind of overcoming this difficulty, and the the way we've been proposing is indeed to use forces. So if our sensor can estimate forces, we can then use these forces in the models that we have available, like bypassing the deformation of the material. Like for example, the forces, like the force distribution on the sensing surface gives you an indication of the torques that you are exerting, that the gripper is exerting on the external objects and so on. So I think like that, again, if we think about the right representation, there are ways of bypassing, for example, the complexity of modeling the deformation of the materials.
Mm-hmm. Maybe it's a simulation here, because you already work about how we can close this gap from simulation to reality. And you mentioned sometimes dynamics in the material is hard to capture sometimes. Can you maybe give more details in depth that how we can maybe close this gap? What kind of maybe parameters or maybe your take about simulation so far for physical simulation of material?
Yeah. So the issue is that I think for complex systems, your simulators can be, very good. You have very good simulation techniques. But, for complex systems, there are so many things that can go wrong, like, asymmetries that you haven't considered, or like non-idealities in the material. For example, you consider it to be a linear elastic or like a hyperelastic even, but then there is viscoelasticity. So it's hard to account for all of these imperfections that we have in the real world. So directly transferring policies from simulation to reality is often not feasible unless you have maybe a low-dimensional system or a simpler system like the one we were using in our experiments. So in this case, I think that a way of tackling this is to try to, again, find an abstraction from, like a state, the classical state and dynamical system, that once we might kind of estimate this state in simulation, we could have another estimator in the real world that estimate the same state. And in this way, there would be a way probably to robustify the process. Like if we have a policy that is based on state rather than on raw data, it might be easier than to perform this transfer from simulation to reality. Now, the ways to estimate the state are different. You could use classical state estimation algorithms if you have some knowledge about the system, or you could use more modern techniques like representational learning that aims to extract automatically relevant information from the data that you already have.
Mm-hmm. Maybe the question again about the sensor design, how to make sure what you do that you get reliable data. You sensor the right data. I don't know if you have encountered that sometimes the sensor maybe fail, or have you thought about how to make sure it's reliable, the data is exactly represented the same as physical touch, for example, force?
Yeah, so the question is essentially like, how do we make sure that our simulations are good enough, like to collect data in such a simulated world? How do we do it? So the first thing we can do is, of course, use most state-of-the-art procedures to collect this, to build the simulation. And the way we did it is we teamed up with people working in continuum mechanics, such that we could really use the latest techniques to characterize a material, and then try to account for the nonlinearities of the material. So we consider our materials to be hyperelastics. And then, of course, we have to test this, how accurate are the simulations, and in our setting, contact setting. And the way we did it is by using force sensors, like classical force sensors, load cells. And we performed a series of experiments with different contact objects, different contact conditions, so pressure, shear, and so on, and try to compare the total force, so the resulting forces measured by our force sensor with those measured in these simulations, or produced by the simulations. And if we get a good match, which was the case, then it means kind of gives you an indication that your simulator is kind of at least capturing the right trend.
Mm-hmm. Maybe I want to take your views about the sensor design again in general. Is there something when you look to the research, maybe in soft robotics, you don't agree? You feel like maybe that's not the right way, or maybe you don't think that's maybe applicable when it comes to sensor design. Do you have any views about that?
Yeah, so this kind of connects back to a point I only briefly mentioned before, which is we're kind of sometimes trying to push in the direction of the sensors that we build, because as I said, like we are still at a point where we are building new sensors because we're still trying to find the right sensing technology. And then what happens is that we really focus on our sensing approach, and we develop techniques that are tailored to our sensor. And I think this is not the right way to go, because it might, as I said before, like be that at some point a new sensor comes in the field and it's kind of disruptive, and everyone is going to use this sensor, and all the techniques that we develop for other sensors might be like unusable. So if we start thinking a different way, like if we think about common representations across all the sensors, that can be estimating a deformation of the sensing surface, forces or contact locations, all these kind of abstractions that really abstract from the specific sensing principle, then the techniques that we develop on top of these abstractions will be reusable over time. And I think we really have to focus a bit more on this.
Mm-hmm. So I want to look at inspiration, and I think that's something you highlighted in your TEDx talk. Do you think there's something maybe missing when we look in reality how human thinking? For example, I found there's many examples in evolution, like spider, how they use the legs on the web to sense or detect a prey or see if there's damage in the web. So there's all fascinating examples about sensing. For you, would you look for these examples and what you try to do you think there's something maybe missing here, or something you imagine that I want to push harder again? For example, you mentioned the example that the thin layer may be challenging for the current camera technology. So I think that's also an excellent point. You mentioned that. What are maybe missing to achieve something that not exactly, but similar to what we have in evolution and across different species here?
Yeah, so I have to say, it's maybe gonna sound obvious, but I'm really inspired by what humans do. Especially what we can already do in the young age. We can already grasp a variety of objects in our young age. If we are carrying a toy, like if a baby is carrying a toy with one hand, they can still use the other hand to manipulate doors, open doors, or like move around any chair and so on. So I see this all the time, and I'm kind of astonished by how far we are with our evolution compared to where we are with robots and the sense of touch. But there is, I think, a very fundamental point that we're probably missing, and I'm not sure if we can do something like this with robots, but I think it would be inspiring at least. And it's the following. So imagine in the human setting, if someone pushes your hand, like your right hand, with something, with an object or with another hand, and if the push is kind of light, you only react with your arm, right? You just move your arm forward, and you can kind of react to this push. But if the push is much harder, such that it can make you lose balance, then you react with all the body. So you probably sometimes move your legs to regain balance, you move your back and so on. So this makes me think that maybe like to make this sensing task, or like sense both perception and action tasks a bit more efficient, we have to think more in a distributed way. So for example, if all these sensors at the hand or the robot hand detect contact, maybe we don't need to have a centralized manner, like looking at contact all over the body to react to this contact. While when balance is compromised, maybe it's then we need like a centralized way, like whole body control algorithm to kick in and just adjust our balance. So I think we could probably go more on a distributed direction with the reaction to sensing, but this is just a very interesting idea. I'm not sure if this will actually be feasible in robots.
Mm-hmm. That's a good point. Maybe since it goes to end, maybe a few questions. I think, since you mentioned distribution, I hear about distributed wave sensing. Maybe I want to ask you when it comes to the redundancy or resilience in the design. I don't know, maybe if we imagining that since in scenario like medical application and the camera would fail, for example, and you need to see how much forces or touch. How do you see a scenario like that to have this resilience or redundancy? maybe multiple camera, but I'm curious about if you look for extreme situation, how you achieve this redundancy or resilience. You mentioned distributed, and I imagine distributed in a sense could be interesting here if I understood correctly. But have you ever thought about this scenario like that? Do you think it's important to consider such a situation like that?
Yeah, it's absolutely important if you really think about applications in healthcare, yeah, it's hard because this can happen. There is a camera failure. There could be a material failure, right? Like your soft material breaks and you have to replace it. And I think the field is largely unexplored. But it's definitely an important aspect to tackle. And I think one way, like the director you can think of, is really having like more cameras trying to cover the same angle with multiple views. You could have some kind of emergency cameras, let's say placed maybe a bit farther away with a lower resolution than on the sensing surface, but that could kick in at least in emergency situations when the high resolution cameras are failing. But I think it would also be interesting just the fact of detecting when there is failure. If the material fails, it's still very hard to detect whether there was a failure in the material with the cameras that we currently have, like with the processing algorithms that we currently have. That would be already a first step, I would say, like first detecting failure and then how to react to this failure. For example, we've been looking at ways to reuse information across cameras such that if a camera breaks, you could just replace it with a new one and just keep using the sensor as you were doing before.
Great. So maybe since your views about how we can use the camera here, maybe I want to ask you in a larger sense here. We have here the material part, and you try to maybe develop models and using camera, an intelligent way to see how the deformation or the kind of sensor to detect. And we also have a smart material, another way. When do you look for the maybe pushing forward the sensor design in general? What makes a good sensor design? There's many here aspects, the material, and you have the models and the intelligent part and how camera can detect that. And also we have a smart material. So when you look to the scope of these choices or spaces, which one do you think maybe need more push here? Do you think the material? Do you think the camera? Which one is significant to you?
Yeah, I think the biggest part is really in the interpretation of data. As you said, like the models to interpret the raw tactile data, because they're like, it's simply like, we don't really know what is going to be useful in the future. We don't know what the right representation is. We don't know what's the best way of extracting physical quantities from the raw data. So there are so many unknown questions there that I think we're going to see a lot in this direction, just simply for the fact that the control algorithms or the planning algorithms that are based on tactile sensing so far are all based mostly on heuristics or very task dependent. So we don't have a systematic approach that we can say, okay, we have a new task in robotics, we have tactile sensors, okay, we're going to do it this way. Let's say, I don't know, the same way you do motion control, right? For example, motion control, you know that MPC is a very effective technique. So you just need to formulate your problem as an MPC or a model predicted control problem, and then you have to find ways of solving the problem. But in tactile sensing, we don't really know like how to use the information for generic tasks. So I think that will be like probably one of the most relevant research directions in the next future.
Great. I don't know if you have maybe a moment of doubt when it comes to maybe the question. You mentioned many interesting question here, as still maybe to answer it, but how you deal with doubt with the approach or the way you think about the design of the sensor, because there are a lot of work you have to do, I think, about in this research line. But how you deal with doubt, if you have a moment of doubt in what you do. Do you have these moments?
Yeah, absolutely. I try to talk to people, I try to get feedback from people, of course, from my advisor, from my colleagues, and from people that sometimes it's even good to get feedback from people that are not really into the field, because they get like a different views on things, because sometimes you are so much into things that you tend to think that maybe some direction is just very interesting only because it's like a simple follow-up of a previous research questions that you were working on. So instead, I think a good approach is to try to put yourself in the position of someone reading the paper of the work that you're planning to do without having read any of your papers before, because in this way you kind of try to make standalone research something that is really impactful, because it can be easily understood by other people and maybe used in other applications.
Do you have any crazy idea when it comes to sensor design? Maybe when we sometimes sit and thinking about something crazy beyond what you really did in the research. Do you have any ideas about sensing that imagine how it looks like for robotics? Do you have this kind of thoughts or visions?
Yeah, I'm quite amazed by camera technologies these days, and I don't know if you probably come across like some endoscope cameras, the ones used for endoscopy. They are so tiny, like really a few millimeters in all directions and all dimensions, and so I was thinking maybe there is a way to create kind of a flexible PCB with a lot of these little tiny cameras around, and you could really have like tactile sensor vision based that would be like really the size of a leaf, or like the thickness of a leaf, and then it would open up a lot of applications. You could cover up an entire robot hand or entire finger. These are interesting approaches, but of course the question is like, how do you handle data coming from all these cameras? And again, the idea would be, can we do this on specific devices, right? I don't know, FPGAs or like even custom boards that could make the data processing on board and then just give you back kind of high level sensing output. So these are like interesting questions, more on the engineering side than the research side. But I think that would be very interesting to address these as well.
Maybe that's a question. What makes you fulfilled and satisfied? And maybe if there's advice maybe it was given to you and stick to your mind, it was a life-changing advice. Maybe what makes you fulfilled and satisfied, and also if I have advice received.
Yeah. Well, I've received many kind of advices during my career, but I think I would mention just some very relevant ones. Already during my master's, I had at ETH, I had a tutor professor that would give me advice during my master's, and he kind of advised me to do my master's thesis in a field or like in a lab that I hadn't done any projects with before, such that I could see how research is done in different places. And I think this was a really, really good advice. And at the time, I was still working in a different field, not in tactile sensing. I was working more on model predictive control or trajectory optimization. Then during my PhD, also my advisor kind of encouraged me to explore, to talk to people in different fields. And that's what I've been doing. I've been talking also with, completely different audience, so like peers, like artists, entrepreneurs, sometimes like going to children demonstration. I think you kind of open your views more and more, and that's how I got into tactile sensing, so completely changing field during my PhD. And I'm now kind of in a setting where when I have something like a topic that I'm not familiar with, I kind of enjoy it. I'm really excited because I take it as a learning opportunity to kind of explore even more the topics that I'm familiar with.
That's good. I can see you're so talented, and I can feel that this is really something, I think, admirable quality.
Thank you.
So I don't know if you have any final words you'd like to say, maybe in the sensing design, your views, any final words you'd like to say?
Yeah, well, I've already said a lot, but I kind of hope, especially on this closing point, that my experience has at least inspired or like encouraged someone to kind of look always beyond their own research field to find interesting research questions and also solutions, of course. And thanks a lot, actually, for leading this conversation. I really enjoyed it, and for me, it's in general very exciting to communicate my research to any kind of audience, but you came up with really great questions, so thank you for that.